I'm very happy to have John Glasser from the CDC here today to speak about transmission modeling and serological surveys against SARS-CoV-2. Thanks, John.
Thanks, Jane, and good morning, afternoon, or evening, whatever it is, wherever you are. I'll be speaking mostly about work that we're doing with Jefferson and Christie. We lead a team that is conducting two large studies of the prevalence of antibodies to SARS-CoV-2 in the United States. These are a bit unusual in that they're rolling studies, and that allows us to do some things that we couldn't ordinarily do with single cross-sectional studies. And if time permits, I'll talk a little bit about between host modeling of immunity. The first of these is work in progress, and while we have modeled the transmission and control of SARS-CoV-2 elsewhere, the second has not yet begun. So we'd be delighted to have criticism. So there are two cross-sectional studies that are underway, and they've been written about in references that I'll list in detail at the end. One of these is a study of blood donations, and that study can distinguish vaccine-induced and naturally acquired immunity. But blood donors don't include children, who, however, are included in the other study, which is sera tested by commercial laboratories for purposes other than evaluating exposure to SARS-CoV-2. And together, these observations provide information needed for age or location stratified transmission modeling. The first is conditions for initializing and evaluating simulation results. And the second is parameters that really can be gotten elsewhere, but this is the gold standard for the forces of infection, attack rates, and probabilities of infection among upon contact between susceptible and infectious people. And what I'm showing you here first are univariate analyses. These are observations. These observations are proportions with antibodies to SARS-CoV-2 assayed by two the more stable assays. These are Roche's Elixis before mid-December clinical diagnostics Vitrios surveys as functions of age on the left and time on the right. The orange curve on the left figures a cubic polynomial, and the blue one is a linear increase followed by an exponential decay that Patty Farrington devised to represent biological phenomena. Absent passively acquired maternal antibodies, these curves should pass through the origin. The regressions are weighted, but too few children were included to evaluate that possibility. The curve on the right figure also is a cubic polynomial, and you can see a little bit of evidence of a decline toward the end, but it's really too soon to tell if naturally acquired immunity is waning. So the first thing we do is we create immune profiles by logistic regression with age and time represented via polynomials. And because those variables are related biologically, all interactions. So these are saturated models. We view models, transmission models as hypotheses, so evaluate them if possible, which it always isn't, before use to inform public policy. And so slices through the resulting surfaces at particular times provide initial conditions for simulations and observations by which predictions could be evaluated. So here are that survey on the left. So this is the proportion immune by age and time in the whole of the United States. And on the right, there are slices through the surface on the left on the 15th of every other month. Just arbitrary times. So that's the first thing these surveys provided. And they also provide the wherewithal for calculating forces or hazard rates of infection that, together with contact rates, permit estimation of probability of infection upon contact. And I would submit that everything else needed for transmission modeling can be obtained from selective review of literature and informed opinion, especially if predictions and observations are compared, discrepancies diagnosed and remedied, and this process repeated until predictions and observations are concordant. And again, I realize that's not always possible, but one thing to note about these surveys is that while immunity does not increase monotonically with age, which precludes the conventional analyses for forces of infection, it does increase monotonically with time. And so what we're doing is when people in the survey for which people are vaccination and infection can be distinguished, we let this expression denote the proportion susceptible among those aged at time t, where the proportion immune, this IB, is immune by virtue of infection or vaccination, or in fact, in one of the studies, infected people can have been vaccinated. So it's really both. And we let the lambdas denote specific rates of infection and immunization in the appropriate intervals of age and time. So then we write the proportion susceptible age I time t as the proportion now at the previous time times e raised to minus the forces of infection and vaccination. And that is to say the probabilities of having escaped, which leads to, by rearrangement, to this expression, and then by substitution for this one. And so then finally writing the forces of vaccination the same way we obtain the forces of infection by difference between the last two equations. It's a bit simpler when there's only, this should not say absent vaccination, so it's only infection here. But we get the same, we approach this in the same way. And this is an example of the surface of the forces of infection now as a function of age and time. From the survey in which children are included, but only antibodies to infection can be detected. And you can see that this increases monotonically with age up to a point, but not with time. And the reason it doesn't include, it declines, is that in the United States, we began vaccinating in mid-December. That's the green curve on the left. And we began with healthcare workers and other essential workers, and then elderly people, and those with conditions that predispose them to serious illness, and then move progressively to younger people. And you can see that in the graph on the right, which presents the proportion immune as a function of age and time. And you can see that immunity increased in December and January, and then especially a little bit later on among older people. So this is the only slide that I'm going to show you that's from the survey that includes both the upload donors. It doesn't include children because I need children for the results and I really want to show you. But there's much more that can be done with this survey. The rest of the figures are from the other survey. So what we do is, now this is not the conventional analysis for obtaining age-specific attack rates. What we do is within any particular age interval, we calculate the attack rates at time t as products of the probability of remaining susceptible at that time, that is having escaped past infection, if it was assessed, as well as vaccination, and the forces of infection, so the product of those two things. And so we can write the proportion susceptible at age t as e raised to minus the integral of the risk of infection plus vaccination from some lower bound, which could be birth, or it could be the introduction of the pathogen into the population up to the present time. So this it denotes the probability of remaining susceptible, and this is its complement, which is the cumulative probability of being immune. If we take the derivative of that, that's minus the derivative of this, which leads to the spores of infection plus vaccination times the proportion susceptible, and we'll write this on the next slide. And further, the force of infection times these proportions of susceptible rates of infection at time t, commonly called attack rates, and similarly for the force of vaccination, those are the immunization rates. So how do we interpret these? At the endemic equilibrium, the fractions on the right of the expression here for the force of infection represent probabilities that that randomly encountered individuals HK are infectious. And if we integrate these rates over discrete time intervals, that gives us a probability density function, the probabilities that individuals have moved from the susceptible state at exactly time t, which enables us to equate these probabilities and that ratio. But this may not be correct in models including vaccination. And this is something that we need to think a bit more about. On the right, we're showing calculations of age-specific now attack rates. I showed you the force of infection as a 3D figure at 3 particular times. One is Thanksgiving of 2020, and then Christmas of 2020, and mid-February of 2021. So just back to this figure. So we have from the serological survey, we have the force of infection, and we have the attack rates. And what we need now are the marginal contact rates and with whom. And we get those from this paper by Pramadal, who used available information about demographic and household surveys and various other metrics, including workforce participation, school enrollment, to develop synthetic contact matrices for countries where studies have not yet been done based on one in Europe. Studies have been done in the US, but the results are disparate, and so we use these instead. And so this is what the marginal contact rates look like in the synthetic matrices for PREM in the United States. And this just separates them out by the 4 settings that they provide. This is the workplace, this is the schools, this is household contacts, and this is other. I'm digressing a little bit, but one of the things, this is a wonderful study in the work that's motivated subsequent improvements have been really important resources for us. But one of the decisions that the investigators made, I understand why they did, but wish they hadn't, which was to count contacts within a day with individual people only once. And so that's why the home-based contacts look like that. But that includes compensating for reducing contacts elsewhere. On the left here, I'm showing you the age-specific contact rates. And the right, if we divide the elements of this matrix by the row sums, we get the proportions of the contacts that members of each age group have with all groups, including their own. So those are the 2 parameters that we needed. We have them all now. We have n equations, each one of which has one unknown, and we can solve them simultaneously for that unknown. And that's what I'm showing you here. These are the probabilities of infection per contact by members of 5-year age groups. And this is a remarkably stable calculation, given the fact that the force of infection and attack rates were very different at Thanksgiving, Christmas, and Ash Wednesday. But this is what we need for transmission modeling. So I see I have some time left, and let me talk a little bit about between host modeling and immunity. So, which those slices through the proportion seropositive permit us to use as initial conditions and to evaluate model simulations. This is a conventional SER model, but it's been modified to include features in the biology of COVID-19 that may be relevant for the transmission of SARS-CoV-2, and in particular asymptomatics, pre-symptomatics. Some symptomatic people are hospitalized, some recover without hospitalization, some recover afterwards, and some die. In this model, immunity is not lifelong. There's a 2-dose vaccination program, and we treat people who have had 2 doses of vaccine. And we treat their immunity as similar to those who recovered from infection. There have been some recent studies that suggest that vaccine-induced immunity is even better than that, but I'm not sure I believe that. So these populations can be, the host populations can be stratified by age, location, or both. And in that case, they're in different groups that are connected by a contact matrix whose n squared elements are the numbers of contacts that members of group I have with members of group J during a period. And I showed you those for the age stratified models contact matrix earlier. In our spatially stratified models, contacts are a function of density, population density as well, possibly of age, within locations and the climate distance between locations. We have some models in which the pathogen population is also stratified, but we haven't yet done a whole lot with those models. What are the challenges of transmission modeling? Well, they're substantial. They're for this pathogen. They are that some of them are that non-pharmaceutical interventions affecting contact rates must be modeled, and these are things like physical distancing, mask wearing, curfews. And in the United States, these were time varying, they were heterogeneous and have unknown, if not unknowable, efficacy and compliance. Serological correlates and the extent of cross protection are unknown, immunity may wane at age-specific rates and so on. And very few transmission models have proven consistently reliable, attribute presumably to the difficulty of surmounting these challenges. And more distressingly, even fewer have improved, suggesting that we need to learn to identify disparities and diagnose and remedy their causes and improve our models. But that's a bit of a digression too. Given these challenges, though, why model transmission? I realize to some extent I'm speaking to the choir right now, but and the reason is that interventions designed to prevent or control infectious diseases have indirect effects, all of them. And transmission modeling is the only way to evaluate their impact. As an example, then I have some experience with vaccination protects unvaccinated people to the extent that vaccinated ones are not, in fact, they do not become infectious and infect them. And I'm showing a figure from some of my own work. It shows proportional reductions over a 5-year period in rubella infections due to supplemental immunization activities during the first month of 3 consecutive school years that vaccinate 5 to 25% of susceptible students entering middle and high school. And the green portions of these bars are reductions among younger and older people. So they are underestimates of the indirect effects. And you can see that they're the same order of magnitude as the direct effects. So these indirect effects can be really substantial portions of the story. And the only way to estimate them that I'm aware of is by a transmission model. So this is a summary slide. It looks like I've gone a little bit faster than I should have. But interventions designed to prevent or control infectious diseases have indirect as well as direct effects. As far as I know, transmission modeling is the only way to assess their impact. As few forecasts of infections, hospitalizations, or deaths in the United States have proven reliable. That may be the case, not be the case elsewhere, but it certainly is in the United States. There are very few that the modeling teams that have contributed to the forecasting or forecasting hub that have been consistently accurate. Evidently, modeling the transmission control of this pathogen presents unusual challenges, and we believe that models should be evaluated if possible, which isn't always the case, but if possible, and discrepancies remedied before use to inform public policy. There's not a whole lot of evidence that that's been going on. And finally, to loop back to the beginning of the talk, these serial cross-sectional surveys provide the information needed to parameterize and evaluate these transmission models. I mean, just cross-sectional surveys provide some of the information needed to parameterize these models. But really, the neat thing about these rolling serial surveys is that we can initialize our models at some arbitrary time and simulate for a while, and then compare results of those simulations to immunity as assessed at that time, and try to diagnose and remedy any disparities and do better next time. And I think that's my next to last slide. I've just got some references. The Beijing and Jones references are to the two serological studies. This was the figure that I just cited, and we made use of the data from Prim et al. This paper by John Ioannidis, I cannot pronounce his name, his Greek name, is very hard on transmission modeling in the US. And the paper by Nils Hens and others has a lot of good, it's a review, but it also has some, both historically and of some more recent work, and some work of ours on mixing and then Patty Farrington. And I think that's my last slide. And all CDC presentations include this obligatory disclaimer that the findings and conclusions of this report are those of the authors and don't necessarily represent the official positions of the CDC and or the National Science Foundation, where the one of the authors is currently the mathematical biology program officer. So I have plenty of time, it looks like, Jane, for questions. I'll leave my slides up in case anyone wants me to flip back to them.
Yep, that's great. Thanks, John. So we can open the floor to some questions now. And I think that while there aren't any questions in the chat yet, but people will have some questions. If you could let me know, so in your equations for force of infection and attack rate, you have your IK variable. Is that your reported cases, or are you estimating some true number of cases somehow?
So I glossed over this, but I is age and J is time. We're just working through the mathematics of how we come to the force of infection and forces of vaccination here. So these are estimates of the proportions immune in one of the surveys by virtue of infection and vaccination, or both, and in the other survey solely by virtue of infection.
Yeah, but how are you estimating II?
Well, II is the proportion infected by virtue of so in this survey, the survey from which this three-dimensional figure and these slices are obtained, it's only infection. So these are the proportions immune by virtue of infection in the different age groups and periods of time. And this is a continuous surface, so we can slice it any way we like. We only have, we don't have exact age, but once you have this continuous surface, you can chop it up any way you want. This is the source of that, the information in those equations.
And so you're ignoring the overlap between vaccination and infection. I'm
not ignoring it. In this particular survey, only one of them is assessed. And then I went on to explain that this decline in the force of infection is due to vaccination. Now, in the other survey, we can actually calculate the forces of infection and forces of vaccination and the infection rates and vaccination rates. The problem with this survey is it doesn't include, the blood donor survey doesn't include children, and I wanted children in order, the goal of this exercise was this, and I needed children to do this calculation. So I apologize if I've switched back and forth, but all of these slides, with the exception of the one showing the increase in with the exception of this slide, all of the data on the other slides are from the survey that assesses only infection, but includes children.
Okay, thanks. Are there any other questions?
Yeah, I have a question. I haven't had a chance to type it in the chat yet, but I'm wondering in terms of there's some evidence, it seems like, from studies indicating that if you've gotten infected by SARS-CoV-2 at some point in time, that as time goes on, the probability of getting kind of a negative serology test, even though you've been infected, increases, right? Because presumably, drop of antibody levels, et cetera. I'm wondering, are you incorporating that possibility at all? So even though kind of immunity is expected to kind of increase over time, if you kind of neglect births, right, into the population, it seems like as time goes on, there might be kind of a systematic underestimation of cumulative attack rate, right? Because
that's a good question. Your question is well taken. There's a little bit of evidence on the panel on the right that maybe immunity is waning. There's evidence from other studies, but and once it becomes very clear that that's the case, we'll have to accommodate waning immunity, but we have not done that yet. Does that answer your question?
Yeah,
it's an excellent point.
It could be that serology test even turns out negative, even though someone could still have immunity to reinfection, right?
So, that's a different question. That's exactly. About serological cohorts of immunity, sure. But one of the things that we did is we eliminated a test that it's the Abbott test that is not particularly stable, and both of these tests are among the tests used in this study. And I think I gave a reference to that paper. Sorry, I should be able to do this more quickly. No, I didn't. But there has been a comparison of the different serological. Serological testing has been a real mess, as you may know. But these two assays are pretty stable. This is a science paper, and I'm happy to send you the reference. I should have listed it. But the Abbott study decays, but we don't know. Antibodies clearly have a role in immunity, but they're certainly not the whole story. And so, the correlates have not been established. So whether immunity is waning or not, there may be some evidence that what these assays measure wanes. But in any case, once that becomes clear, yes, it does need to be taken account of. What we'll have is a dynamic process between the creation of immunity and its waning, which is the situation in other diseases, pertussis, for example.
Okay, thanks. I think we have time for one more question. Ed, did you want to ask?
Sure. Yeah, I typed it in the chat, but maybe I can explain myself better verbally. The people have tried, of course, to estimate the true rather than just the reported number of cases, incidents, as a time series of incidents, using the time series of deaths together with our best idea of the infection fatality ratio. And this work here that you're reporting on gives us another way to probe that. And of course, we know that the reported cases were only a small tip of the iceberg, certainly early on. Have you looked at how the estimates of the actual underlying true incidence from your work compare to what other people, what people have tried to do using the infection fatality ratio?
You're absolutely right, Ed. And we have not, but one of our co-authors, Dr. Jones, does discuss that in his recent JAMA paper. But the answer is 2 to 3 times as many infections, or a little bit more initially than currently are occurring than infections are reported. That's certainly one of the challenges in with any disease. There's a spectrum of illness, but it does seem that there is a a much larger proportion of asymptomatic and mild symptomatic disease in this case. But anyway, Dr. Jones and his colleagues estimate that somewhere between 2 and 3 infections are actually reported. And I'm aware, by virtue of some of my international work, of studies that are toward the 3 end, but a lot of publications are toward the 2. I mean, we're seeing only half, but that may be an underestimate. But 2 to 3 is a good range.
Thank you.
Good question. All 3.
Thank you. Thank you so much. I think that we can leave some more questions to the discussion panel. And next, we're very happy